Okay, students. So now we have discussed the geometrical optics. I am sure you have understood what different types of mirrors are. We discussed three types: the plane mirrors and undercurved mirrors, the concave mirror and the convex mirror. Thereafter, we saw how refraction of light takes place when it travels from one medium into another medium. And then how different lenses refract light and form images. So, I am sure you know the different types of images formed by mirrors as well as lenses and the characteristics of these images. And you know plane mirror is a certain type of mirror that forms specific images, whereas the concave mirror and convex lens forms many different types of images based on the position of the object, whereas the convex mirror and the concave lens forms only one type of image irrespective of the position of the object. And also you all have a good understanding about the refraction of light when it travels from one medium to the other, from a denser medium to a rarer medium or rarer medium to a denser medium, and how total internal reflection takes place. And with all these concepts, the applications and the uses of light and the different types of mirrors and lenses to us. And you are very familiar with drawing ray diagrams. So now I am going to discuss the questions given in your textbook. So I am sure you have already answered these questions. Now you are going to check whether you have answered them correctly. And I am sure you would have got it correct. So the first question under exercise 5.2. Name two types of mirrors that always produce virtual images. Answer the following questions regarding the image formed when an object is placed between the mirror and the focal point of a concave mirror. Is the image upright or inverted? Is the image larger than the object or smaller than the object? Is the image real or virtual? When the object is moved toward the pole of the mirror, will the image become smaller or larger? So, all the properties related to the image. At what object distance do you get the largest image from a concave mirror? Is that image upright or inverted? Place an object in front of a convex lens at different positions and observe the image in each case. Write two properties common to all those images. So now I will move on to the first question. Name two types of mirrors that always produce virtual images. What are virtual images? Images that cannot be obtained on a screen. So there are two mirrors that form only virtual images. So you have to remember, students, here they are asking always produce. So even the other mirror produces virtual image but only under certain instances. Here it's always. What are they? You know the answer. The plane mirror never forms a real image. And the convex mirror doesn't form a real image. So, the plane mirror and the convex mirror always form virtual images. So, the answer to this question, name two types of mirrors that always produce virtual images. It is plane mirror and convex mirror. So, they produce images that cannot be obtained on the screen, virtual images. I will move on to the Next one. Answer the following questions regarding the image formed when an object is placed between the mirror and the focal point of a concave mirror. So, when you read the question, students, you all have to see whether it's a mirror or a lens, then what type of a mirror. So, here it's a mirror and it is a concave mirror. You know what a concave mirror is? The reflecting surface is curved inwards. And then you have to remember the position. It is between the mirror and the focal point. So, when we have the object between the mirror and the focal point, what type of an image is formed? You all can remember. Is the image upright or inverted? Is the image larger than the object or smaller than the object? And is it real or virtual? So, if you are not sure about the answer, then what you can do is, you can draw a ray diagram. So, let me do that for you all first. It is always better if you are not sure about the answer to draw the ray diagram. So, here we start by drawing the principal axis. You don't have to go into a detailed diagram where you measure distances. You need to understand the nature of the image. So, then we have to have the line for a concave mirror. And here you can remember it's a concave mirror. So, let's say this is the focal point. So, the object is between the mirror and the focal point. So, let's say the object is going to be here. This is the object. What will happen to the ray that is coming towards the mirror? You all know how they reflect. So, here as I said, I am not drawing according to scale. This is to understand the way the images form. So, when you all draw proper ray diagrams, how do you draw? You have to use a thin, sharp pencil, and also you have to use rulers to get straight lines. So, here I am going to use the straight line option to draw the line. So, a ray coming parallel will reflect through the focal point. So, this is how one ray will reflect. Another ray that is coming along the center of curvature. Let's say if I take this distance and this distance, they are the same distance. So, a ray coming through the center of curvature will go without any change. This is a ray. So, it has to refract at this point. So, you can see a ray coming parallel to the principal axis, reflects through the focal point. A ray coming towards the center of curvature reflects back in the same path. So, here you can see they don't meet on this side. They will only meet on this side of the mirror, that is behind the mirror. So, what do? We use broken lines to extrapolate the rays. We use a broken line to extrapolate the ray, this ray and this ray. So, here you can see they meet at this point. So, if I mark the image that is from here. So, this was the object, this is the image. Here, object between mirror and focal point. So, now can you see the properties. What are the properties? It is an image that is larger than the object and it is in the same direction. So, it is a upright image. Upright, larger than the object, and when it is behind the mirror, can you get it on the screen? No. So, then what type of an image is that? That is a virtual image. So, now you know the characteristics of the image. So, students, when they ask you a question, I am sure you all have very good memory. So, you remember what the characteristics of the image are. But at that moment, if you can't remember the characteristics of the image, you know how to draw ray diagrams. So, immediately you draw a ray diagram like this. Here, as I told you before, I didn't draw anything according to scale because I just wanted to show you all the properties. So, this is how we get the image. Then you can answer the questions. Now, we will go back and answer the questions. Right. Is the image upright or inverted? So, you saw it was an upright image. Is the image larger than the object or smaller than the object? It was larger than the object. Larger than the object. Is the image real or virtual? It was inside the mirror. So, it was virtual. It was a virtual image. The next one. When the object is moved toward the pole of the mirror, will the image become smaller or larger? I am sure you observed this during the activity, but you may not be sure. Then what do? You have to draw the ray diagram to check, or else if you can remember, you can answer the question. So, let me show you all with a different color in the same diagram. Then you can easily understand how the change takes place. So, here I will use a different color to show the object. Now, initially we had the object here. Now, according to the question, the object comes closer to the mirror. So, let's say the object will be somewhere here. The object will be somewhere here. So, that is the next object. Again, the ray coming parallel to the mirror will reflect through the focal point. So, it's going to be the same ray. A ray coming parallel will reflect through the focal point. So, this is going to be the same ray. Another ray that is coming through the center of curvature, that will reflect back in the same path. So, again I have to draw another ray coming through the center of curvature, but here you can see the path changes. A ray coming this way reflects back also in the same path. So, what do we do now? We have to extrapolate the two rays. So, when I extrapolate the rays, here you can see they meet at that point. So, therefore, the image will form here. So, the same object but closer to the mirror. Image also comes closer to the mirror, and what happens to the size? It becomes a little more smaller. But still, it is an upright image and a virtual image. So now you can understand what happens when you bring the object closer to the image. So as I said again, students, for the exam, they won't ask you to draw two ray diagrams like this together. But here I did that so that you know the same positions, the F and C are in the same positions and the same object, so you can compare how the image changes. So again, object between mirror and focal point, but closer to the mirror. So now if we answer the question, when the object is moved toward the pole of the mirror, will the image become smaller or larger? What has happened? It becomes smaller. So you can easily answer the question. Smaller, or we can say becomes smaller. Becomes smaller. So always, students, when you are not sure about the answer or if you are confused, you can always draw the ray diagram. Even if you know, it's always better to draw the ray diagram and check and confirm the answer before writing it down. So now you know when we bring the object closer to the concave mirror, the image becomes smaller when the position is between the mirror and the focal point. With that, I will move on to the next question. At what object distance do you get the largest image from a concave mirror? Is that image upright or inverted? So to answer this question, students, you have to think about all the different images that are formed by the concave mirror when the object is kept at different positions. So just now we discussed one image. Where was the object? The object was between the mirror and the focal point. And what was the nature of the object? It was upright, it was virtual, and it was bigger than the object or larger than the object. So that is one instance. What happens when you move the object towards the mirror? The image becomes smaller. So what happens when you move it away from the mirror? It becomes larger. So you can keep on moving it away from the mirror. The image will be virtual and larger than the object. But when the object is on focal point, that is F, what happens to the image? It forms at infinity. What are the properties of that image? We can't see that image, but you know the characteristics. It is very larger than the object and also it's an inverted image. So there we get large images, but when it is between mirror and focal point, we can see the image. We can see it inside the mirror. But if it is at infinity, we cannot see the image. But we know that it is very larger than the object. So here, if we look at the question, at what object distance do you get the largest image from a concave mirror? So the question is largest image. If it is largest image, although you can't see, it has to form at infinity. So the object has to be on focal point. So to answer this question, when the object is on F, that is focal point. Here the image is the largest image. What type of an image is this? upright or inverted? It is inverted. So, it is an inverted image. But the only thing is, we cannot see the image. So then, if we look at the image that is larger than the object image, but we have observed, where do we place the object? Like I said, when the object is between the mirror and focal point. So, here we can see this image. What type of an image is this? Is it upright or inverted? It is an upright image. So, this is an upright image. So, students, here since they have asked for the largest image, obviously you all know when we move it away, when the object is on F, that is focal point, that will be the largest image. But when we did the activity, we could not see the image. Here, when it is between the mirror and focal point, you were able to see clearly that the object, the image was larger. So, that is how we answer this question. Then I will move on to the next one. Place an object in front of a convex lens at different positions and observe the image in each case. So, think about the images formed by a convex lens. You all know you can keep the object on one side, the lens in the middle, and there are different types of images. How does it form? When it is between the focal point and the lens, the image will be larger, that is an enlarged image, it's upright, and also it is a virtual image. You cannot get it on the screen. But when you keep it on F, that is focal point, what happens to the image? Again it forms at infinity. Between F and 2F, the focal point and twice the focal length, what happens to the image? You get a again enlarged image, but it is inverted and real. Then what happens to the image when the object is on twice the focal distance? Same size as the object, inverted and real. And when you take it away from twice the focal length, what happens to the image? Again, it's a real image, but it becomes diminished, smaller than the object, and still it is inverted. So, there you can see the characteristics of the image varies with the position of the object. We have observed this during the activity as well. So, to answer the question, place an object in front of a convex lens at different positions and observe the image in each case. Write two properties common to all those images. Now, when we discuss the properties, did we come across any common property? All the properties are different. Why? Either it's enlarged, virtual and upright, or it is at infinity. Otherwise, it's real, enlarged and inverted, or the same size, inverted and real, or diminished, inverted and real. So, you can see the characteristics are changing. So, for a convex lens, if you are asked to write two properties common to all those images, only thing is, except for the position when the object is on F, all the images form on the principal axis. That's how we draw the ray diagram. But that is not a common property. That is how the image formed. So, here we cannot actually write two common properties for the image formed by convex lenses. But just think of the convex mirror. What is the nature of the image formed by the convex mirror? Now, instead of convex lens, if they had asked convex mirror. So, here let's say we will consider a convex mirror. Now, a convex mirror always forms a same type of image, irrespective of the position of the object. What type of images are formed by a convex mirror? Always it's smaller than the object, and it is virtual because it forms inside the mirror, and also it's upright. So, those are the properties of the image formed by a convex mirror irrespective of the position. So, if I write down the properties here, this is going to be upright, virtual and larger than object. So, remember students, when we use a convex lens, the nature of the image or the properties of the image depends on the position of the object. But when it is a convex mirror, irrespective of the position of the object, they always form the same type of image. With that, I will move on to the next question. What is meant by the term refraction of light? Draw ray diagrams to show how refraction occurs when light enters a dense medium from a rare medium. A rare medium from a dense medium. I am sure you can draw those. Name the rays and the angles of the following ray diagram. So, here you can see this is the activity that we did in the lab. Refraction of light through a glass block, a block of glass. So, you have to label the different rays and the angles. So, I am sure you have already answered these questions. Now, I will write down the answers. The first one, what is meant by the term refraction of light? So, here refraction of light. What is refraction of light? When the light rays travel from one medium into another, because their speed changes, there is a bending of light. That is known as refraction of light. So, here if I write the answer, bending of light when it travels from one medium into another medium due to difference in speed of light. So here, bending of light when it travels from one medium into another medium is known as refraction of light, and this is the reason why refraction happens due to difference in speed of light in different mediums. So I will include that as well. Light in different mediums. Different medium. So that is the reason. You can even stop your answer at this point. Bending of light when it travels from one medium into another medium. But you have to say that the light rays bend. The next question. Draw ray diagrams to show how refraction occurs when light enters a dense medium from a rare medium from a dense medium. You know how refraction takes place. So here from a dense medium to a rare medium and the rare medium to a dense medium. So to answer the first one. So a dense medium from a rare medium. So the light ray is going to travel from the rare medium into the dense medium. So then we have to see how the refraction takes place. Do we draw a ray perpendicular to the interface? No. Why? Because there will be no bending. So it has to be a ray that is incident with an angle. So let's say this is the incident ray, and at the point of incidence there will be the normal. So what is this? This is the incident angle. Now when it is going from rare to dense medium, how does it bend? It bends towards the normal. So here this ray will bend towards the normal. So here you can see this is the angle of incidence and that is the angle of refraction. Angle of incidence will be greater than angle of refraction. Why? It bends towards the normal. What is the next one? A rare medium from a dense medium. Just the opposite of this. So here we need to have the dense medium first. And here we have the rare medium. So then what happens? Again we will consider a ray that is incident at an angle. This is the normal at the point of incidence. So when it is going from dense to rare medium, what happens to the ray? It refracts away from the normal. So that is the angle of refraction and that is the angle of incidence. So you can see the difference. When it goes from rare to dense, refracts towards the normal, bends towards the normal. When it is from dense to rare, away from the normal. So here what is the relationship between I and R? R is greater than I because it refracts away from the normal. So that is how you show the ray diagrams. Then the next question. Name the rays and the angles of the following ray diagram. So here you all know this activity. What happens? That is the incident ray coming from air, then into glass and again out into air. So there are 2 points where the refraction takes place. So let's see. What are the rays? From A to B, that is the incident ray. Incident ray. Why? It comes from air and is incident on the glass cube. Then what happens here? It bends. So BC is the refracted ray. So here BC is the refracted ray. Then we have CD. This is the ray that comes out of the glass cube. What do we call it? The emergent ray. Emergent ray. Then we have the angles. What is the ABX angle? What is this angle? This is the angle of incidence. Then this one is the angle of refraction. Again, what is this angle? Angle of emergence. This is also another angle of refraction, and this is the angle of emergence. So here if we label the angles, ABX, that is I, angle of incidence. What is the next one? YBC. YBC, that is R, angle of refraction. So here you can see from air to glass, rare medium to a denser medium bends towards the normal. Glass to air, dense medium to a rare medium bends away from the normal. So what is this? NCD, that is the angle of emergence. So those are the different rays and the angles you see in this diagram. I am sure you have labeled them correctly. The next one. The figure shows different light rays entering a rare medium from a dense medium. So it's coming from the dense medium and going into the rare medium. So here you can see they have not completed the ray diagrams. Copy these figures and complete the ray diagrams. What is meant by the term total internal reflection? Give an example for a situation where total internal reflection occurs. So I am sure you can do it by yourself first. Now I will move on to the first question. The figure shows different light rays entering a rare medium from a dense medium. So we need to find out how the refraction will take place and complete the ray diagram. Copy these figures and complete the ray diagrams. So here it has already been copied for you. So if you all are doing it, you have to copy it in your writing book and complete the ray diagram. So here I am going to do it on the diagram itself. Right. So what is this? The ray starts from water, a dense medium, into air, the rare medium. So when it goes from a denser medium into a rarer medium, what happens? It refracts away from the normal. So this is the normal line that has been given to you. It will refract away from the normal. So here you can see the angle of refraction is larger than the angle of incidence. Then what happens here? You can see the angle is larger here and it is given to you as critical angle. What is a critical angle? The angle of incidence when the angle of refraction is 90 degrees. That is, the light ray refracts through the interface. So here, since this is critical angle, it will refract through this interface. That will be the refracted ray. And here you can see the angle of refraction is going to be 90 degrees. Then what happens here? The same thing, the angle is greater than critical angle. So when it is greater than critical angle, what happens to the light rays? They don't refract, but they reflect internally. And what do we call that? Total internal reflection. So here it is going to be total internal reflection. Here again, students, since I am showing what happens to the ray diagram, I didn't measure the angle and draw the reflected ray. Instead, I have shown what happens. So students, here you can see initially when it goes from water to air, it refracts away from the normal. You can see the angles. This is the angle of incidence, angle of refraction. And when it is critical angle, that is given the symbol C, the angle of refraction is 90 degrees. And if the incident angle is greater than the critical angle, there will be no refraction. Instead, there will be total internal reflection. So that is what I have drawn here. And you can see I didn't measure the angles because this is to show what happens to the ray. But if you all are drawing a proper ray diagram, you know that you have to use very sharp pencils and a ruler to draw straight lines and thin lines so that you can get the proper image. But here we are just showing how refraction will take place. So we have done this question. I'll move on to the next one. What is meant by the term total internal reflection? That is what we saw before. What happens there? When the light ray travels from a denser medium into a rarer medium and angle of incidence is greater than critical angle, then there will be only reflection, and that is known as total internal reflection. So we have to write that down as the answer. When light rays travel from a denser medium into a rare medium and the angle of incidence is greater than the critical angle. The light rays reflect within the denser medium. This is known as total internal reflection. So this is how you have to write the answer for this question. What is meant by the term total internal reflection? So here you have to mention the rays going from the denser medium into a rare medium, and you have to say about the critical angle. When the incident angle is greater than critical angle, there the reflection occurs within the denser medium. So, this is to explain what total internal reflection is. The next one. Give an example for a situation where total internal reflection occurs. You all can remember a few examples where total internal reflection takes place. Can you think of those examples? One good example is the optical fiber. Where do we use optical fibers? In endoscopes, we use optical fibers, and in telecommunication and internet cabling, they use optical fibers for transmission of data. And also the same optical fiber is used as ornaments, where the ornament gives a nice glow, attractive glow. And the same thing can be used to make different objects that are used in stage performances. So, all these use optical fibers. So, here they have asked, give an example for a situation where total internal reflection occurs. So, we can simply say inside the optical fibers or in optical fibers. So, to make it a more clear answer, I can say when light travels through optical fibers. So, they have asked an example, one example. So, common one is the optical fibers. I will move on to the next one. Draw a ray diagram to show how an image is formed when an object is placed in front of a convex lens at a distance greater than twice the focal length. So, students, when you read a question like this, what are the things you have to look into? The object in front of a convex lens, whether it's a lens or a mirror, and what type of lens or a mirror. Then the distance of the object. Then only you can draw the proper diagram. So, let's say, is that image real or virtual? So, this is related to the properties. Describe a simple activity to find out whether the image is real or virtual. So, it has to be real or virtual. Is that image smaller or larger than the object? So, everything has to be done once we draw the ray diagram. Here, they have said to draw the ray diagram as well. So, now I will move on to the questions. Draw a ray diagram to show how an image is formed when an object is placed in front of a convex lens. So, as I told you, you have to know what the optical device is, convex lens, at a distance greater than twice the focal length. So, those are the two important things that you need to remember. Right. So, how do we start? We start with the principal axis. So, I will draw the principal axis here. Then we need to draw a broken line for the lens. So, here I have the broken line for the lens. And what type of a lens is this? A convex lens. So, we have to draw a convex lens there. So, what do we do after that? We have to draw the focal length and twice the focal length, or we have to mark the 2 points. So how do we mark it? We can mark it on either side of the lens. Why? There is a focal point on either side of the lens. So to do that, here they have not mentioned the focal length. So you can mark any point. Normally I take the 5 centimeter as the focal length. So here I'll mark a point at 5 centimeters, another 5 centimeters for twice the focal length. Again on this side also 5 centimeters. And another 5 centimeters for the focal, twice the focal length. So what do we do there? We have to write the points. This will be F and F dash. Here also we have F and F dash. Then where do we place the object? It has to be greater than twice the focal length. So to do that, I will use a different color. So here it has to be twice the focal length. That is the object. And we can label it as O. Next we draw the ray diagram. How do we do that? We need to use two rays that are coming from the top of the object. So for that, I will take one ray as coming parallel to the principal axis. Parallel to the principal axis. So a ray coming parallel to the principal axis, you have to bring it to this point, and also we have to mark the direction of the rays. How does this refract? It goes through the focal point. So here it goes through the So now we can draw a ray that is refracting through the focal point. It will go through the focal point. That is the refracted ray. So here also you have to show the direction. What is the second ray? We can use a ray that is going through the optical center, or else the ray that is coming along the focal point, so that it will refract parallel to the principal axis. So I have to get a ray that can go through the focal point. So to do that, so now if we draw the ray that will go through the focal point. So here, starting from this point, going through the focal point. That is the second ray. How does that refract? It refracts through the How will this ray refract? It will refract parallel to the principal axis. So now I have to get it parallel to the principal axis. So here this will be the ray. So here you can see the two rays meet at this point. This is the refracted ray. A ray coming parallelly goes through the focal point. A ray going through the focal point gets refracted and travels parallel to the principal axis. And here they meet and form the image. So this is going to be the image of the object. So this is the image and that is the object. So draw a ray diagram to show how an image is formed when an object is placed in front of a convex lens, distance greater than twice the focal length. So you can see the characteristics of the image. So the next question under this, is that image real or virtual? So it is on this side of the lens. Can you get it on the screen? Yes. So that is a real image. So a short answer, real. Then we will look at the next question. Describe a simple activity to find out whether the image is real or virtual. How do you do that? What is a real image? Image that can be obtained on the screen. So how did we see these real images? By holding a screen and observing the image on the screen. So here, describe a simple activity to find out whether the image is real or virtual. So to write down the answer there, what do we write? So now we have drawn the ray diagram. You know the position of the object and the lens, and you know where the image forms. So you have the object at a distance greater than twice the focal length. You place the lens in a stand. You place it at a fixed point, and on the other side of the lens, we hold the screen. It can be a screen or a white paper. What do we do after that? We adjust the white paper or the screen so that we get a clear image. So once you get the clear image, you can confirm that it is a virtual image. So describe a simple activity to find out whether the image is real or virtual. So here, if we write down the activity, place a convex lens on a stand and place. So here for the object you can say object, or normally what do we use? We use a lighted candle. So I will say lighted candle. Lighted candle at a distance twice distance greater than. We use the position greater than twice the focal length. Hold a screen on the other side of the lens. Adjust the screen to get a sharp image on the screen. Then it is a real image, or you can confirm that it is a real image. That is the simple activity. The next one. Is that image smaller or larger than the object? Now, it was a convex lens. When you have a convex lens, you can remember the ray diagram that we drew. I will go back to that slide. Here you can see that is the object and this is the image. Normally, when the object is on to twice the focal length distance, you get the same size image. But when the object is further away from twice the focal length distance, then the size of the image decreases. And when you take it further away, the size decreases further. So here you can see it's smaller than the object. So to answer the next question, is that image smaller or larger than the object? It is smaller than the object. So you have to say smaller than the object. What is the other name given for an image that is smaller than the object? We call it the diminished image. Now I will move on to the next one. The figure shows a light ray entering an optical fiber. So here you can see they have shown a part of the optical fiber and one surface is labeled as B and they have shown a light ray that is A, and here you can see AR and optical fiber. Draw a ray diagram to show what happens to that ray inside the optical fiber. So you know what happens to rays inside optical fibers. State what changes occur to the speed of the ray as it follows this path from the source. Calculations are not required. So you just need to explain. At what object distance do you get the largest real image when an object is placed in front of a convex lens? Write down two other properties of that image. At what object distance do you get the smallest real image when an object is placed in front of a convex lens? So, I am sure you have already answered the questions. I will write down the answers now. So, the figure shows a light ray entering an optical fiber. So, this is the light ray. Here you can see the light ray and it is incident at the point B. And you can see the optical fiber. Draw a ray diagram to show what happens to that ray inside the optical fiber. So, here also we can show it. So, what is going to happen? Now, this is the point of incidence. So, there will be the normal. At that point, here we have the air medium. Optical fiber, you all know either it is glass or a certain type of plastic. It's a more denser medium. Air is the rare medium. Optical fiber is the denser medium. So, what will happen to the light ray? It will refract towards the normal. So, here it will refract towards the normal. But when it is incident at this point, what happens there? The angle of incidence is greater than the critical angle. So, what will happen to the ray? It will undergo total internal reflection. So, the ray will reflect like that. Total internal reflection. Again from this point, total internal reflection. From here, it travels through the optical fiber in a manner where there is total internal reflection taking place. Why? always the light ray is incident with an angle greater than the critical angle of the optical fiber. So this is how the light ray travels through the optical fiber. Even with the bendings, it can undergo total internal reflection. The next question. So, state what changes occur to the speed of the ray as it follows this path from the source. Calculations are not necessary. So, here what happens? Why does it bend at point B? Because in air, there is a speed for light, and when it enters the optical fiber, there is another speed. So, there is a change in speed at point B. But once it goes into the optical fiber, there is only reflection. If there is reflection, that means there is no change in medium. It's within the same medium. So, the speed does not change throughout the fiber. And afterwards, when it is coming out of the fiber, again there will be a change in speed. So, that is what we have to write here. State what changes occur to the speed of the ray as it follows this path from the source. So, here we can say at point B, that is the point where you have the normal light refracts when it enters the optical fiber from air. So, here due to the difference in density of air and optical fiber, there is a change in speed of light. But once it's traveling through the optical fiber, it travels with the same speed. So, here throughout the optical fiber or through the optical fiber, there is no change in speed. Then what happens? When it comes out of the fiber, there will be a change in speed. Again, when light exits the fiber into air, speed will change. Speed will change. So, in the above diagram, we showed how the light ray enters the optical fiber up to the end point. We did not show how it comes out of the fiber. But you all know again there is a change in medium from denser medium to a rarer medium. So obviously there will be a change in speed. With that, I will move on to the next one. At what object distance do you get the largest real image when an object is placed in front of a convex lens? So it has to be the largest image and it has to be the real image in front of a convex lens. So try to remember the characteristics of the images formed by convex lenses. We change the position of the object, the characteristics change. When it is far away from the object, what is the size of the image? It's a small image. We drew a ray diagram before also. But when you bring the object closer, it becomes larger. And on twice the focal length, it becomes the same size as the object. And when it is between focal length and twice the focal length, you get a larger image. But when it is between the lens and the focal point, there also we get a very large image. But what is the difference? When the object is between focal point and twice the focal length, it is an inverted image. But when it is between the lens and the focal point, it's an enlarged, that is larger than the object, and it is upright. But you can't get it on the screen. So it's a virtual image. So there are instances between f and 2f, you get a larger image, but it is inverted and real. Whereas between lens and focal point, still you get an enlarged image, but it is upright and virtual. So I explained two types of images where you get an image larger than the object. But here we will look at the question again. At what object distance do you get the largest? The important thing is real image. So when do you get the real image? When the object is between focal length and twice the focal length, f and 2f. So that is where we get the real image. So here we have to write the answer as between focal length and twice the focal length. So that is when the image is real and larger than the object. Next one. Write down two other properties of that image. So you have to write two other properties. We already know it is larger than the object, that is enlarged, and it is real. So we have to write two other properties. What are the other properties? Is it inverted or upright? It's inverted. So we have to say the image is inverted. Inverted. What else can you say? Where does the image form? It forms on the other side of the lens, and where? Away from twice the focal length. So that is another property that we can give. You can say forms on the other side of the lens away from twice the focal length. So you can remember, students, when the object is close by to the lens, the image forms at a longer distance. But when you move the object away from the lens, the image comes closer to the lens. Next one. At what object distance do you get the smallest real image when an object is placed in front of a convex lens? At what object distance? And you need to say the smallest real image. How do we find the focal length of the lens? By focusing an object that is very far away, something outside the window, so that parallel rays come from that object and they all converge on the focal point. So there we get a real image, but it is the smallest real image. So at what object distance do you get the smallest real image when an object is placed in front of a convex lens? So here it has to be far away. So we can say either far away object or at infinity, or you can say it is, yes, it is better to say it as infinity, so that you get the smallest image on the focal point. So here object at infinity, or we can say very far away object. So then you will get the smallest real image on the focal point. With that, I will move on to the next question. A bag contains lenses with focal lengths 10 cm, 20 cm and 25 cm, which are not marked with their focal length. Describe a simple activity to identify the three types of lenses. The three types of lenses. So here what do? We know they are all different lenses, but you can identify whether it's a convex lens or a concave lens by looking at the surface. So we will consider these as convex lenses. So then we don't know what has what focal length. So what can we do? We need to have a screen. So screen is where the image will form, and if we focus the light rays coming from a far away object, where will the image form? It will form on the focal point. So what we can do is, we can place a screen in a certain fixed place, and we can have the lenses at different distances. So if I show it in a diagrammatic manner, maybe we could just draw a line like that, and then we mark this point where we have the screen. We are not going to change the position of the screen. So that is going to be there all the time. Then we need to know the different distances. So here I will have to mark the different distances. 10 centimeters, 20 centimeters and 25 centimeters. So here 10 centimeter mark, 20 centimeter mark and 25 centimeter mark. Then we need a stand, or you can even hold the lens with your hands, and what is the object that we are going to use. It has to be a far away object. Say a tree outside the window, a very far away object. So the rays that come from that object will be parallel to the lenses. Then what do? Say we take the first lens, keep it at this distance 25. See whether we can get the clear, inverted, real, diminished image on the screen. If you can get it clearly, but still you have to confirm that it is the focal point. So you move the lens to the 20 centimeter mark. Again try to get the image and then again move it to the 10 centimeter mark and try to get the image on the screen. So if for the lens at 25 centimeter mark you get the sharp image, that is inverted, diminished and real, then that will be the focal length of that lens. Likewise, we repeat the activity with all three lenses. Place it at the three different points and try to get the clear image on the screen. Don't move the screen and try to focus the far away object. Then you know what is what. So that is a simple activity. So you have to describe a simple activity. This is what I have explained to you. So you have to describe the activity. So here first I can say place a screen at a fixed point. Then second one, mark 10, 20 and 25 centimeter points as shown above. Then what do? Focus So let's say place one lens on the three different points. And identify the point that gives the clear, diminished, inverted image on the screen, and that will be the focus or focal point. That point is the focus. Then what do? We repeat the activity. Repeat the activity with the other two lenses. So then you can find the focal length of all three lenses. So I am sure you can write this answer And I'm sure you would have already written an answer like this. Now we will move on to the next one. Light changes direction when it passes from air to water. That is refraction. Give the name of the process that produces this change of direction. So that is the answer. Explain why this change of direction occurs. The diagram shows some fish underwater and a butterfly above water. So here you can see a butterfly and two fishes labeled as A and B. So water and air. Draw a ray to show the path of a light ray traveling from the butterfly to the eye of the fish. So coming from the butterfly to the fish. Explain what critical angle is. Explain how rays from fish A could reach the eye of fish B through two different paths. Draw rays in the diagram to show these two paths. So those are the questions. Now I will discuss the answer. Light changes direction when it passes from air to water. Give the name of the process that produces this change of direction. How do we call it? We call it the refraction of light. Refraction of light. Explain why this change of direction occurs. So we have to explain what happens there. So we have to say, what do we need to say? When light travels from one medium to the other, what happens to the light rays? The speed of light rays changes. And if the light is faster in one medium, we call it the rare medium, and the lesser speed is known as the denser medium. So because of this change in speed, the light ray bends from its path at the point of incidence, and that is known as refraction. So explain why this change of direction occurs. So here we have to say, when light travels from one medium to another, the speed of light changes. Therefore, the light ray bends at the point of incidence. So explain why this change of direction occurs. So we have said it bends at the point of incidence. So that is the change in direction. There will be a change in direction of the light ray. So that is what happens there. Then I'll move on to the next one. The diagram shows some fish underwater and a butterfly above water. So you can see all those here. Draw a ray to show the path of a light ray traveling from the butterfly to the eye of fish B. So here is the butterfly, this is fish B. They want you to show how the light ray comes from the butterfly to the fish. So here what is this medium? This is the air and water medium. Which is the denser medium? What is the rarer medium? This is the rare medium and this is the dense medium. So what happens to the light ray? They come and bend towards the normal at the point of incidence. So here I have to show the light ray coming from the butterfly, and here we will have the normal at the point of incidence. This is the incident ray and it will bend towards the normal. So it will reach the eye there. So if we show the angle of incidence, this one, and angle of refraction, this one. So draw a ray diagram to show the path of a light ray traveling from the butterfly to the eye of the fish. This is the incident ray. So here they have asked us to draw the path of the light ray, incident ray and the refracted ray. If you like, you can also label it, but here we need to show the path only. I'll move on to the next one. Explain what critical angle is. What is critical angle? When light rays travel from a denser medium into a rare medium, they refract away from the normal. So when you increase the angle of incidence, what happens to the angle of refraction? That also increases. And at one point, the angle of refraction becomes 90 degrees. That is, the light ray will travel through the interface between the two media. At that point, the angle of incidence is known as the critical angle. So that is what you have to explain here. So we have to say when light travels from a dense medium to a rare medium, it bends away from the normal. With increasing, I can write it as angle of incidence as I, the angle of refraction R also increases. When, or we can say, the angle of incidence when the angle of refraction is 90 degrees is known as critical angle. So that is how you explain critical angle. Then we have the next question. Explain how rays from fish A could reach the eye of fish B through two different paths. Draw rays in the diagram to show these two paths. So first we have to explain what happens here. Now fish A is here, fish B is there. They are both in the same medium and light can travel through water medium. So from fish A, it can travel to fish B directly. That is one path. What is the other path? The light rays from A can go this way. They can travel upwards. And then when they are incident at the interface, air-water interface, what will happen? There will be refraction. But when the angle of incidence is greater than the critical angle, then of course there will be total internal reflection. So that ray that is reflected at this interface will reach fish B. So those are the two paths. One is the direct traveling of the light ray, the other one due to total internal reflection. So here we have to explain how rays from fish A could reach the eye of fish B, and also you have to show the rays. So first I will show the rays and then I will write the explanation. So from the fish to the eye of the fish, the light ray can travel. The second method, I will use a different color. So here the light ray from the fish can incident on this surface and can undergo total internal reflection. So there again it can reach the second fish. So again students, I am just showing the path. I am not drawing according to scale. You all know when you draw the ray diagram, the angle of incidence and angle of reflection have to be the same. So here if I redo that, say a light ray coming to this point can, so here it is almost the same, but when you draw with the ruler and measure the angles, you can get a proper ray diagram. So this is just to show the path how light travels. So one is, we have to explain this as well. So one way, this is the first method, light travels through water directly. And if I mark this as the second method, second way in which the light ray travels, what happens there? Light that is incident with an angle greater than the critical angle undergoes total internal reflection and reaches fish B. So the two paths in which light rays from fish A reaches fish B. So since they have asked us to draw the rays as well as explain, I have done both here. Now I will move on to the next one. A student carries out an experiment to investigate the refraction of light as it passes from glass into air. He shines a ray of light through a glass block and into the air as shown. So it's shown here, glass block and air. This is one ray, that is the other ray, and this point is marked as X. Complete this diagram and show the angle of incidence I and the angle of refraction R. Measure these two angles, and we have to write down the angles here. And the last one, the student increases the angle of incidence and notices that above a certain angle, the light no longer passes into air. Explain this observation. I am sure you know the theory of this activity and the observation, and you can give the explanation correctly. So now I will move on to the answers. A student carries out an experiment to investigate the refraction of light as it passes from glass into air. So that is what is shown to you. He shines a ray of light through a glass block and into the air as shown. So that is this diagram. Complete this diagram and show the angle of incidence I and the angle of refraction R. Measure these two angles. So here we need to complete the diagram. What do we need to do? We have to draw the normal. Why? The incident ray is shown to you and the refracted ray is also shown to you. So now we have to draw the normal and also we have to measure these two angles. So to do that, what I will do is I will use a protractor. So here we can have the protractor here, and if I have it this way, it's convenient for me to draw the normal line. It has to go through the point of incidence. This will be the normal line. So then it's easy to measure the angles. Here you can see this is the angle of incidence and this is the angle of refraction. So since the protractor is there, I can measure the angle of refraction. So to do that, I will just rotate the So here we can read it easily also from this point. So when you all do it in your writing book, you will be drawing very thin lines. So you know it's very easy to measure the angles. But here the lines are thick. Still I will take it as from this point. From 180 up to 145. So that is going to be an angle of 35 degrees. So this is going to be an angle of 35 degrees. So here if I rotate this and move it to this point, so here again, this is the angle of incidence. So this is 180. So here it's about 165. So that is an angle of 25 degrees. So that is the angle of incidence, 25 degrees. So here you can see glass is a denser medium. and air is the rare medium. So, angle of incidence is 25 degrees, and when it enters the air medium, it refracts or bends away from the normal. So, that is why the angle is 35 degrees. So, complete this diagram and show the angle of incidence I and the angle of refraction R. So, this is going to be angle of incidence I and that is angle of refraction R. So, I is going to be 25 degrees and angle of refraction is 35 degrees. So, that is what you have to show here. Since they have asked us to show only I and R, even if you don't write the 25 degrees and 35 degrees there, that is okay. You can just mark this as I and R and write the values here. That is also okay. So, now I will move on to the next one. The student increases the angle of incidence and notices that above a certain angle, the light no longer passes into air. Explain this observation. So, you have observed this before as well and you all know the reason. What happens here? When light rays travel from a denser medium into a rarer medium, they refract away from the normal. And when you keep on increasing the angle of incidence, what happens there? The angle of refraction also increases. And at one point, the angle of refraction will be 90 degrees. That is, the light ray will pass through the interface. Thereafter, what happens? When you increase the angle of incidence more than the critical angle. The critical angle is when the angle of refraction is 90 degrees. So, when the angle of incidence is more than critical angle, light no longer refracts. Instead, it undergoes total internal reflection. So, that is what you have to write here. So, here the question is, the student increases the angle of incidence and notices that above a certain angle, the light no longer passes into air. So, here you have to mention about that particular angle. So, we can say when angle of incidence is increased, angle of refraction increases accordingly. When the angle of refraction is 90 degrees, the I is known as critical angle C. So, above C, that is after above a certain angle. So, this certain angle is C. So, above the critical angle, above C, light no longer refracts. Instead, it undergoes total internal reflection. So this gives you a complete explanation of what happens there. Why or how light refracts and how the refraction angle increases with the angle of incidence and it becomes the critical angle, and above critical angle when you increase the incident angle, the light doesn't refract, instead it undergoes total internal reflection. With that, I will move on to the next question. The figure shows a light signal traveling through an optical fiber made of glass. So here the figure is given to you. You can see it's a glass fiber, optical fiber made of glass. So what happens? This is the ray that is incident on the glass fiber and the point B is the point of incidence where you have the normal. So outside it is the air medium and there it's the glass medium. So how are they known as, or what is their density? The air is the rarer medium, glass is the denser medium. So how does light bend? It bends towards the normal. You can see that there. Then what happens? It incidents at point P. At point P, the angle of incidence will be what? It will be greater than critical angle, so that there will be no refraction. Instead, there will be total internal reflection. So that is what is happening here. So we'll look at the question. State two changes to light. It should be two changes to light when it enters the fiber from air at point B, or state two changes that occur to light when it enters the fiber from air at point B. So we have already discussed one change. What is that change? It bends towards the normal. And why does that happen? Because the speed of light in air is different from the speed of light in glass. So the speed of light changes at point B. So those are the two changes. They have asked for two changes. So one we can say light bends towards the normal. One change. The second change, we said there is a change in speed of light. Does it increase or decrease? It's going into a denser medium. So the speed decreases. You can either say there is a change in speed or you can say the speed will decrease. So I will say the speed of light will change, and within brackets I can say decreases. So that gives you a complete answer. The next question. Explain why the light ray after hitting point B travels along the path shown. So this is also something that we have already discussed. What happens at point B? The light is incident with an angle greater than critical angle. You have to give that in your answer. Therefore, it does not refract. Instead, it undergoes total internal reflection as shown in the diagram above. So that will be the answer. At point P, the light is incident with an angle greater than the critical angle of glass. Therefore, it does not undergo refraction, but it undergoes total internal reflection. So that is the answer that you have to write here. You have to say at point B, the incident angle is greater than the critical angle. So that is why there is no refraction. Instead, there is total internal reflection. With that, I will move on to the next one. Lenses are used in many optical devices. So that you know, we have discussed so many different examples. Complete the table below by writing information about the images formed by each optical device. So here in the table, they have given different optical devices. Eye, projector, magnifying glass, and here they have given the nature of image. So for the eye, it's a real image. That is why the image forms on the retina. Then the size of the image is given to you. You have to fill that here. For projector, it's magnified, and also for magnifying glass, they have given the position of the image further from lens than the object. So the rest of the information has to be filled by you. So that is the first question. Then B part, the figure shows an object placed in front of a convex lens at a distance less than its focal length. So here you can look at the figure. They have marked the focal point F dash, and the object is between F dash and the lens. So the lens is denoted by this arrow, double-headed arrow. And on this side you have the other F, because for lens we have focal point on either side of the lens. So here the person is looking at the object from the other side. Complete the ray diagram and draw the image formed. Use your ray diagram to describe 3 properties of the image. So that is after drawing the ray diagram. I am sure you can do this first. And now I will discuss the answers. Lenses are used in many optical devices. Complete the table below by writing information about the images formed by each optical device. So you know the devices, eye, projector, magnifying glass. We have to fill these information, nature of image, size of image, and position of image. So the first one is eye. You all know that we look at all the things that are around us using the biconvex lens present in our eye. And the image always forms on the retina. So that is why it's a real image. But you all know all the objects are of different sizes. There are many objects which are very, very large. But still we get the image on the retina. So that has to be a image that is smaller than the object. So, the image will be diminished or smaller than the object. So, the first one is size of image. So, we can say smaller than the object. Or in other words, we can say it's a diminished image. Then where does it form? Position of the image. The position of retina will not change, but always the image has to form on the retina. How does that happen? The curvature of the biconvex lens can be adjusted so that always the image forms on the retina, real image smaller than the object. Then what will be the position of the retina? You all know from all the ray diagrams that we have drawn, it has to be between focal distance and twice the focal distance. So, position of image is between focal length and twice the focal length. Then the next one, projector. We don't use projectors that much now because we have the multimedia presenters and the overhead projectors. But even if you consider those multimedia presenters and the overhead projectors, you have seen it's fixed at the higher elevation, maybe from the roof, the ceiling, they fix the projector and you see the enlarged image on the screen. So, if it is on the screen, what type of an image is that? It has to be a real image and it is larger than the object. That is the reason for using a projector. Those days we had the normal projector where we place the slide or the transparency sheet on the projector and the image forms on the screen. But the modern ones are all through the computer. You can feed all the information. Everything is obtained on the screen. So, either way, it needs to have a lens. And the image has to be real. So, it has to be a real image. That is why we are able to see it on the screen. And it is magnified. So, if you want to have an image that is real and magnified, where should the object be? The object has to be between focal length and twice the focal length. Then only the image will be larger. So, here in order to get a magnified real image, how do we place the object? The object has to be between focal length and twice the focal length on one side of the lens so that the image forms at a distance greater than twice the focal length. Then only you will see a magnified or larger than the object image. So, here they have asked for the position of the image. That will be away from twice the focal length. So, that is, we can say, away from twice the focal length. That is for projectors. Then we have the magnifying glass. How do you look at images? Using a magnifying glass, we have the book. We hold the magnifying glass closer to the book so that the book is between the lens and the focal point. So, then what type of an image do you get? Is it a real image? Can you get it on the screen? No. It's going to be a virtual image and it has to be upright. the same direction, and also the purpose of using the magnifying glass is to enlarge the image. So, it will be an enlarged or magnified image, or you can say larger than the object. And it is going to be further from lens than the object. That is on the same side as the object. So, here we need to write the nature of image. Nature of image is going to be virtual. You cannot get it on the screen. And the size of image is going to be either magnified, or you can say enlarged, or you can say larger than the object. Same way, for an image smaller than the object, you can call it diminished. So, these are the properties of the images formed by these different optical devices. I am sure you got them correctly. Now, I will move on to the next question. The figure shows an object placed in front of a convex lens at a distance less than its focal length. So, we have the object here, the figure is given to you. Complete the ray diagram and draw the image form. So, here we have to complete this ray diagram. You can see this is the focal point. So, here one ray is going parallel to the principal axis, and here you can see the other ray going through the optical center of the lens, and this is the lens. So, what will happen to these rays? The ray that is going parallel will refract through the focal point. So, we have to draw one such ray. So, to do that, I can either use the ruler. Here, since I have the facility of drawing the straight line, I will use that. You all have to use a sharp pencil and a ruler to draw the straight line. So, here the ray that is parallel to the principal axis will go through the focal point. So, here we have to mark the direction of the ray. That is the refracted ray. Then the ray that is going through the optical center will go through the optical center continuously. It does not undergo bending. Why? That path is perpendicular to the surface of the lens. So, it is perpendicular to the surface of the lens. Therefore, the path does not change. So, that is going to be a straight line again. This is the ray that will continue in the same direction. I will start drawing from here so that I get the proper line. So, here you can see they are both going away from each other. So, therefore, the two rays won't meet. So, what do? We use broken lines to extrapolate the rays. So, I will first extrapolate this ray and then the second ray. So, the image will form at a point somewhere there. So, here we have you will have this line will go like this. So, here we have the image. That is the image and that is the object. So, this is like using the magnifying glass or the hand lens. The image is larger than the object, that is magnified or enlarged. It's upright, that is the same direction. Can you all get it on the screen? No. So, therefore, it's a virtual image. Virtual, upright and magnified. So, we have completed the ray diagram and got the image. The next one, use your ray diagram to describe three properties of the image. So you can see all the properties there. We need to describe the properties. What are the properties? One is enlarge. So you can see this is the size. This is the size of the object. So to describe, we can say magnified or enlarged image. Enlarged image. Then it is the upright image. Upright image, and also it is a virtual image. So since they have asked for 3 properties, I have written these 3 properties: magnified, upright and virtual image. There is one more. That is the position of the image. What can you say about the position of the image? It's further away from the object, on the same side as the object. So that is also another property that you can explain using the diagram. So here these are the properties of the image formed when the object is between focal point and the lens. So now I will move on to the next question. The figure shows an object OB in front of a convex lens. The 2 focal points are marked as F and F dash. An image of OB will be formed on the right of the lens. So here we have the lens. The object is shown as OB, and this is the focal point on this side and the focal point on the other side. And it says an image of OB will be formed on the right side of the lens, that is on this side, because rays will travel like this and refract towards the other side where the image will form. And here you can see the object is away from F. So it has to be between F and twice the focal length. Focal length and twice the focal length. Draw 2 rays from the top of the object B that pass through the lens and reach the image. Draw the image formed and label it as I. Calculate the ratio of the image size to the object size. So here you can see a graph paper is given to us, so it's easy for us to calculate the ratio. We can count the number of boxes and calculate the size of the image and the object. Then we can calculate the ratio between the image and the object. Okay then. So now I will draw the image on this. So here you can see the object is here. So how do you draw the rays? From the top of the object, and there has to be 2 rays. So that's what they have said. Draw 2 rays from the top of the object that pass through the lens and reach the image. So here I need to use the line as well as I will need to use the ruler. But we don't even need a ruler to draw this line if it was on a line of the graph. But for y'all, you will need a ruler. So I will use that here. Right. So the ray that is going parallel to the principal axis. How does that bend? It bends and travels through focal point. So from here, it has to go through focal point. I will draw a longer ray. Then we will consider a ray that is going through the optical center. That will also go straight through the optical center. It will not undergo any type of bending. the two rays have to meet or intersect at a point for us to get the image. So the ray going like this goes without bending. So here we have that ray. Now I will mark the two rays, the ray coming parallel, the ray going through the optical center, and it refracts at these two rays. So then we need to have the image. So the image forms at this point. The image forms at that point. So we need to draw two rays from the top of the object that pass through the lens and reach the image. That we have done. Draw the image formed and label it as I. I have drawn the image. We have to label it as I. Calculate the ratio of the image size to the object size. So here if we count 2, 4, 5, 6, 7, 8, a little more than 9. So it's between 9 and 10. So we can take it as 9.5 boxes. And on this side, if you calculate the number. So I will say here, I will take it as 9.5 boxes for the object. And on this side, we have 2, 4, 5, so 10. And after that, there are almost 4 boxes. So it's 14 boxes there. So what is the ratio between they have said to calculate the ratio of the image size to the object size. So it has to be image divided by object size. So the image, we take it as 14 and the object is about 9.5. So roughly if we do a calculation, we can take it as 14 divided by 10. So that is about 1.4 times larger. Or if you do the proper calculation, it will be almost equal to 1.5 times larger than the object. So anyway, you can show that it is a magnified image. So if I do the calculation, it will be between 1.4 and 1.5. So when you all draw it with very thin lines, that is why I am giving you all the two different values, a range. I have drawn lines, you can see they are thick lines. So I didn't calculate the size exactly from the point because of the broad lines. But when you all do it, you will be able to draw very thin lines and measure the length accurately. So it will be between 1.4 or 1.5, 1.5 times greater than the object. Or what you can do is you can measure the height. So here you can also use the ruler and you can measure the height. But since they have given us the graph paper, we don't really have to measure it. This comes to about a little, again you have to keep it accurately. So it's about 2.3 centimeters. If I write that there, it will be 2.3 centimeters. And the same way, if we calculate the height of the image, that is about 3.3 centimeters. So 2.3 and 3.3 centimeters. They are also, you can calculate the difference. 3.3 divided by 2.3 centimeters. So again you will get a similar ratio. So students, if they give you a graph paper like this, you can either count the boxes, that is very convenient to us, and get the ratio. They have only asked for the ratio. If they have asked for the height, then you have to measure and give. Here it is the ratio. So you can either count the boxes and calculate the ratio, or you can measure the height and calculate the ratio. So that is what we do for this question. I am sure you did it correctly and you also got the same ratio. Now I will move on to the next one. The diagram shows a convex lens forming a real image of an object. So here both the object and the image are shown to you. So here you can say object is between focal length and twice the focal length, whereas the image is away from twice the focal length, and so you can see the object is comparatively smaller than the image. So it's an enlarged image and it is upside down, so we call it the inverted image, and also you know it can be obtained on a screen. So it is a real image. So when you look at a ray diagram like this, immediately you should try to get the information. Try to recollect what type of an image is formed there. State two changes that occur to the image when the object is moved towards F. What will happen to the image when you bring it towards F? As the object moves closer to the lens, image moves away from the lens. So the image will move towards that side. It will move further away from twice the focal length. And what will happen to the size of the image? That will also increase. So you know it will become a larger image and it will move further away from twice the focal length. So here you need to state two changes that occur to the image when the object is moved towards F. So that is what you have to write. The first one, image moves further away from 2F, or you can say twice the focal length. That is one property. The second one, image becomes large. So you know when the object comes closer to the lens up to focal point, the image will go away from twice the focal length and it will become large. So those are the changes that will occur to the image when you move the object towards the F. With that, I will move on to the next one. The diagram shows an object placed at O in front of a convex lens. So here you can see the diagram, students. That is the convex lens and the object is here. What is the position of the object? It's between focal length and the lens. Focal length of the lens is 30 millimeters. So here they have given you the length. O is 20 millimeter from center of lens. So the distance between this and F is 30 millimeters and between the center of the lens and object is 20 millimeters. And the object is 15 millimeter high. So here we have to draw a ray diagram using the length and the height. So we need to take measurements. by drawing this diagram to a suitable scale. Find the position of the image. So, as you know students, so far we have not drawn a ray diagram according to a scale. We have drawn many ray diagrams, you have practiced, but not according to a scale. Now, we will do that. Then state two properties of the image. So, once you draw the ray diagram, you can easily write the properties. By measuring the heights of the image and the object, find the ratio of their heights. That we have done before also. So, first we will have to get a suitable scale. So, you can see the focal length, that is F, is 30 millimeters and the object distance is 20 millimeters and the height I will write it as H, that is 15 millimeters. So, if you look at all the values, you can see 30, 20, 15. So, what I will suggest is we will take a scale where we take 5 millimeters as 1 centimeter. So, that will be the scale. Then you have to write that down. So, scale is what? 5 millimeters equals 1 centimeter. So, then we can calculate the focal length, the distance of the object from the lens as well as the height. Then it will be easy for us to draw the ray diagram. So, I will do that calculation first. So, the focal length, because it's 30 millimeters, we will divide it by 5 millimeters. That will be equal to 6 centimeter. Then the distance of the object is 20 millimeters. So, divided by 5, that will give you 4 centimeters. And finally, the height. Height is 15 divided by 5, that is 3 centimeters. So, now that we have all the values, these are the values that we have to use. We will draw the ray diagram. So, to draw the ray diagram, what do we need first? The principal axis. I will draw the principal axis here. After that, what do? We need to draw a line to show the lens. So, that has to be a broken line. Then it is easy for us to identify as well. So, I will have that line here. And also, we have to denote that this is a convex lens. So, all that is okay. Then what do? We have to mark all these points. So, here we need to have 6 centimeters for focal length. So, twice the focal length will be 12 centimeters. So, here at the right. So, 12, this part where you have 6 and the 0 point, that is 2F, F, and we need to have it on this side as well. So, at the 18 mark we have the F again, and the 24 mark we have 2F there. So, if I mark those points, if you can remember students, this side is it was marked as F dash. So, I will also write this as F dash and this side as 2F dash. So, this will be F and this will be 2F. Then what do? We have marked the 6 centimeter marks. Then the object is at 4 centimeters from the lens and you saw it was on this side. So, here we need to mark the object. 4 centimeters from the lens. So it has to be at this point, and we need to have a height. The height of the object is 3 centimeters. So to do that, so this is the point where we need to have the object. That is the object. So now we have the object. I will label it as O. Then what do? We need to draw the rays. But if you can remember, students, they have shown us 2 rays. The ray going parallel to the principal axis and the ray going through the optical center. So we will also use the same type of rays. So a ray going parallel to the principal axis. So if I draw that first, I will use a different color for that. Then it's easy for you all to understand also. So here a ray going parallel. How does that refract? It refracts through the focal point. Right. So this is how it is going to refract. It will refract through the focal point. So that is one ray. Ray that comes parallel goes through focal point, and the other ray is going to be through the optical center. So we have to draw a ray that is going through the optical center. So those are the 2 rays. But what happens to this ray? They don't meet on this side. You are very familiar with that. So we extrapolate the 2 rays. So to do that, I will use the broken line. I will make it as long as possible. So that is one ray. Then we have to extrapolate this ray as well. So there we can see where the object forms. This is the point where the 2 rays meet. So here I have drawn the image of the object. We have to show it using the arrowhead. So that is the image. Object is between the lens and F, focal length, but the image is away from 2F, but it is behind the object or further away from the object. Then what do we need to do? We have drawn the ray diagram according to scale. Let's check the question. State 2 properties of the image, and also by measuring the heights of the image and the object, find the ratio of their heights. So that is what we have to do now. We have to first state the properties. So that is the B part. What are the properties? It is a magnified image. And also you can see it's upright. What is the other property? They have asked for 2 properties. You can think of more than 2 properties. One is magnified or enlarged, erect, and it is virtual. So you can write that as well. So since they have asked for 2, I will leave it at that. Magnified image, upright image. So then we need to measure the heights. So here I have the ruler. So if we take the measurement, this is 9 you can see 9 centimeters. And we have already taken the height of the object, that was 3 centimeters. So here you can see, just by looking at the values itself, you know what the ratio will be. So I will calculate the ratio. C part ratio, that is between image and object, that is 9 centimeters divided by 3 centimeters. So it's going to be 3. So the image is 3 times magnified than the object. Do you need to convert this scale to the real values? No need. Why? Because we took a scale. So according to the scale, we drew the diagram and the measurement is also with the scale. Since we are only calculating the ratio, we don't need to calculate the real value. Even if you do, you will get the same ratio. So here we will be multiplying the 9 centimeter by 5 so that we get the value in millimeters. It will be 45 millimeters, and 3 into 5, that will be 15 millimeters. 45 divided by 15 also gives you the same ratio. Since we are going to multiply both by 5, we don't have to do that here. So if they had asked you to find the height of the image, then you measure it as 9 centimeters and you have to multiply by 5 so that you give the value in millimeters. But here, since they have asked for the ratio, we can directly substitute these 2 values. So that is the answer for the question. Let me go back and confirm whether we have written all the answers. Yes, we drew the ray diagram, then we wrote 2 properties of the image, and then we have calculated or found the ratio between the image and the object. Okay, students. So with that, I have come to the end of discussion on the exercise in your textbook. So this was the last question in your textbook. So I'm sure you were able to answer all the questions by yourself, and then you checked your answers with my answers, and I'm sure you got everything correctly. But that is not enough. You have to keep on practicing more questions. Try drawing ray diagrams and practice for all the lenses, as for both the lenses as well as the 3 different mirrors.